this talk will be quite a bit shorter than the 30 minutes I originally planned, because I planned to have a discussion about the attribute. However, that was solved at the IPA BOF, but more on that later. So first, what's the problem statement? What are we trying to solve? On the slide, you can see a very complicated test case that utilizes the OpenMP parallel for class, and the function test takes an integer c, which is then being used in the class in the for loop as a bound. Now, how is this actually being processed? When the pragma gets expanded, the for loop gets outlined into its own function, as you can see here. The kernel we are actually trying to optimize is then the function test.ompfn, which is being called by the function comparallel. Now, we are interested in IPA, so let's look at the call graph. What does it look like? This is what it looks like. The function test is calling gomp parallel. However, the kernel itself doesn't have a call site, which, that's an issue. Where is this call site? Oh yeah. It's actually in the function gomp parallel itself, but that function, its code, is actually in a runtime library. GTC doesn't see the call site. Is this fn, parentheses data. We need to expose this call site. This is what the call graph actually looks like. Right, so let's solve this. Let's expose the call site. For this purpose, I implemented a new attribute called callback, or, well, not anymore, more on that later. And the semantics of this attribute are, when you annotate a function with it, you are basically saying this function primarily calls one of its arguments, and that's pretty much it. It doesn't hide the pointer, it doesn't edit it in any way. Pretty much it's a shell function for the callback itself. Now the syntax of the attribute is, the first argument is the index of the function, and then in order, the arguments of the indirect call. So if I go back, gomp parallel is annotated with the callback attribute with arguments 1 and 2, right? So the first argument, 1, means that fn is being called. The 2 says that the only argument is the data pointer. Right. To represent the attribute in the call graph, we have to introduce a new type of edge into the call graph called a callback edge. Now, this edge is purely imaginary. It doesn't have a size, it doesn't have a time, because the edge really doesn't exist in the program. It's purely symbolic for the optimizer. However, it does allow us to actually optimize the callback function. Now, with this edge, we can do some interprocedural analysis. But first, we have to implement some infrastructure for the edge. So if, for example, constant propagation was successful and we call the callback function, the edge gets redirected, to this .constprop clone. That's how we optimize. Now, how do we represent this redirection? In the code, the original call to gomp parallel looks like this, and it's using the now outdated function test.ompfn, and that's not correct. We need to replace this address with the address of the clone. Right, and that's pretty much it. That's redirection done. Now, what can we do with this? Well, the improvements to IPA are, first of all, constant propagation is actually working now. So this is an actual test case that I'm trying to get into the GCC. And I don't really know how to show this. This is just a dump that actually says that we do, in fact, propagate the value 100 to the kernel itself. But that's not all. We do have some improvements to ICF. So originally, when you perform ICF on the kernels, what happens is that a single unified body is created, and the body of each callback is replaced with a direct call to this unified body. So the call graph looks something like this. There is an indirect call from the dispatching function to the callback, and then a direct call to the common body. But now, because we can we can replace the address in the call itself, we do get rid of that direct call. So the common body is actually being called indirectly. Now, what does this do? Well, we save a single frame per callback, and if all the conditions are met, like the callbacks have internal linkage, they are static, they are not used anywhere else, we can actually delete them. So how big are the savings in terms of space? Well, if you unify like 10 callbacks, we are talking about maybe 200 bytes in binary size, which is not groundbreaking, but it's at least something. Now onto performance, really nothing changes. And actually small PT slowed down by maybe like 0.5%, but that's probably just an artifact. Yeah, it's underwhelming, but that's just the way it is. It's still like very early in development. Now onto Clang. Clang actually implements the attribute since Clang 9, which is now probably like 6 or 7 years old. Now we do, this is where the IPA BOF sort of comes into play. There I claimed that the attribute is implemented, but it actually doesn't work. Turns out that's not really true, and it was just a skill issue on my part. I couldn't get it to work. I couldn't achieve the speedups that they claimed at Euro LLVM. However, a fellow approached me yesterday, Edward Zingerman, who actually got it working. It's really cumbersome and it's not documented well, but it actually is working. Now, as stated yesterday, the attribute in Clang actually doesn't follow the same syntax. It uses a different syntax for the this pointer, and it allows identifiers as arguments. This is a very quick summary of the differences. The main difference is that for the unknown value, Clang uses -1 instead of 0. I use the format attribute as sort of a reference, because that's where GCC and Clang actually come together and implement the same thing. I use it as sort of a standard. So instead of 0, Clang uses -1, and instead of 1 for this pointer, Clang uses 0, which introduces a lot of problems. But yeah, this is where I plan to propose some solutions on how to fix this discrepancy. However, that was solved yesterday at the IPA BOF, where it was agreed that we'll rename the attribute to callback_only, and that solves the issue. Right, so patch status, what does it look like? It's still not merged to trunk. We are currently on V4, or well, V3. I have to produce the V4, but it is written. I just have to bootstrap it. In the patch, the attribute is actually named space callback to take it out of the public API in the same manner as, for example, fnspec. However, that will be changed to callback only to allow users to use it as well. Well, on to future work. Once we get it merged, the first order of business will be replacing some fields in the cgraph edge class with summaries. Because right now, there are additional 2 bytes to link attributes and edges together, and that's really wasteful. But yeah, the patch is already long enough, so I saved it as an incremental change. Then what I want to do is extend some glibc functions with the attribute. For example, you can annotate qsort with it, or pthread create, which is actually a perfect use for that. And then we can extend some side effect analysis. We can support member pointers, an std function, also lambdas, also if and assume. However, that's really into the future. What's also planned is allowing signature changes for the dispatching function. What that means, if if the compiler does have access to the body of the dispatching function, and for example, I don't know, performs something like SRA or constant propagation, the signature changes, and suddenly the indices in the attribute don't align, which is an issue. Right now, the way I fixed it is I just removed the attribute and pretend like nothing happened. However, this is subject to change, and I do want to recalculate the indices. Also, right now, when it comes to gomp task, it does use the attribute, but it only uses it when the copy function is not needed. Because propagation through the copy function is pretty complicated, but it can be supported in the future, and I would also like to add automatic detection of the attribute. Right, so that's it from me. I'd like to thank Honza Hubička and Martin Jambor for their mentorship and patch reviews, and I would also like to thank the GNU Toolchain Fund for making this talk and my attendance possible. Right. Do we have any questions?
I have a question, but maybe not so much to you as to Thomas and Tobias, since we have them in the room, and maybe Jakub and anybody else. We have finally this groundwork necessary, almost ready. I believe it's going to be merged soon, so we'll have the core graph edges. And as Josef said, he measured, he didn't measure any speed up on any benchmark that he tried. So what should we look at? Because you mentioned IPA in the performance section of your OpenMP talk. So do you know of any test cases where probably something should be propagated from the outside of the OMP context to inside of the OMP context, that perhaps doesn't work yet, but we or Josef might get it working. Something to look at. Because another thought on the same topic is that currently the propagation works. I mean, if you can put back the slide where the constant is propagated. I think just before that, where you showed that basically the constant is being loaded from an artificial structure that is being passed to the outlined kernel. Right, here it is, and this works because the jump functions already have support for things passed by reference in a structure, but I'm slightly afraid. But it only works if it is if there is a single load. If it's like a basically scalar loaded from a structure passed by reference, or by value, that doesn't matter. But we do not follow two loads. So if what we send to the outlined kernel is itself a structure, or probably an array descriptor in Fortran, We are probably not able to encode that in, well, we are not able to encode that in the jump functions. So hopefully that is something, if we get that working, that might help with performance, because, you know, in Fortran arrays are, and all the important strides and sizes are encoded in the descriptor. And of course in the C++ programs, a lot of the information is actually passed and encapsulated in some, you know, structure. So I hope that might be a way to get some speed up somewhere. But if you can, if you find an opportunity like that, it seems that you're not aware of any at the moment, please let us know. Please Josef know, and I'm interested as well. But yeah, so there is a limitation of jump functions that makes this like good enough, that makes them good enough for this case. But when there are two loads involved, it doesn't work, and that's probably something that will need to be solved, even though it may need quite a bit more of computational power during compilation. And it would rely heavily on alias analysis, of course. And it also revives again, sorry to be stealing the time, that the idea of marking the structures that we create to pass data to the outlier kernels as something like initialized only and then never overwritten, so that the jump function construction can just look at the...
It's not that the whole structure is never overwritten, but we, at the OpenMP lowering time, know this field in the structure is input only, this, and this field in the structure is passed by value or passed by reference, and this is the output only, and this is input output. And we can use them many times in the kernel. It depends. Sometimes we use the decal value expr and just emit it all the time, because it depends on if you read. If it's, for instance, a scalar, then we just load it once, and that guess works well. But if it's passed by reference, then yeah, we need to refer to it all the time. And if it's input only, input output, then we of course need to reference use that field all the time, because we can change it in the structure. So definitely we could mark the fields. It wouldn't be generic for the attribute couldn't do it, but if we find it is past structure marked this way, we could use it. If it's
I think it would be
for
useful, because on alias analysis, we currently rely on like the alias analysis to make sure that that interleaving stores don't confuse the jump function construction. So yeah, I actually haven't checked how big of a problem it is, but I think it has high potential to be useful. And then probably the jump function itself needs to be enhanced to be able to handle two loads. But yeah.
Can the patch currently handle stuff like VRP propagation, or do we handle it only for scalar arguments, and because this is always by value?
Perfect point. No. For the so-called aggregate jump functions, we only do constants, and that's probably something that would be easier to enhance and to do. It would consume. It potentially could consume quite a bit of memory, because the jump functions there are many of them. But yeah, but it is, and this is again a great use case probably.
Maybe do it only for the marks.
It appears that your feature is it's actually not OpenMP specific. You're talking about, like, propagating the IP information across callbacks and so forth. So that's why you listed all the applications, the future directions that you said at the end of your talk. For the OpenMP situation, there's actually a much simpler solution. That is, we should do the outlining only and not expose the gomp parallel call so early.
That's not possible.
Why? Why?
Because all the optimizations just completely destroy all the rules. We need to rely on the code to be close to the source, and as soon as we go wild, then you just can't do all the required OpenMP checking. And
we can mark the function as an OpenMP child function, but we don't have to expose the gomp parallel call.
We've tried and it never worked. Really, the current position in the pass queue have been played with, and it's really very early because we couldn't make it work elsewhere.
You'll have to be more elaborate on that.
Well, if you want to try it, you're welcome, but it would take years and that.
Or maybe first to the question of test case, I think we have to check. I mean, there could be some. What my feelings, I have not really tried it and exactly looked at it. It seems to be as if going to offloading. I think we mark them as no cloning and so on. That might be an issue. I mean, at the end, we only rely on the order of the table that they are for the offload side and the host side exactly the same item in this list. So replacing them or adding the other one instead of first one works. But my feeling is that it's currently with how it's cloned and so on not working for target or OpenMP target or for the kernels or parallel, because the way the function are marked and we need to put them in. I think it shouldn't be, I mean, we might need some special casing, but that would be limiting the way we get it in offloading.
Does the generation of the offloaded functions happen after whole program analysis with LTO, or does it work with LTO actually? And if it's so, is it produced after? Well, basically, are they subject to the whole program phase of the constant propagation? These target regions that get offloaded? Do they? Because I don't know what the sequence of when things are streamed out at what point? Is it like pre-WPA, the whole program analysis, or post?
Exactly.
Sorry? It's...
But the LTOs, the offload streaming, I think, happens at the same time as the normal LTO streaming out. So.
But there are two streaming outs. But probably
No, but we don't have VPA for or WPA. It was discussed that we needed.
And I mean, my feeling is that essentially what is done works, but one needs to make sure that the same node is used there, and I think the attribute can't be prevented. I mean, it's only called once. I mean, you kind of clone the function, but then you don't use the other one. So in that sequence, it perfectly works, but I think some attribute and other things prevent that it gets actually used. So we need to see how to kind of special case that it actually works. I think the analysis by itself shouldn't be really the problem, and having them in the list and so on, or all those should be fine, but I think some extra step is needed to enable it.
probably not only one.
Yeah.
Yeah, thank you.